Okay, good morning everybody. I hope everyone's having a wonderful day. My name is Dan, of course, and I hope you're having a great day. It's Friday. Isn't it Friday already? Man, this week went a little fast, right? So just as a reminder, remember that assignment 2 is out there. You can complete most of it, except for the stuff on Heaps. We're going to be doing that the next couple of lectures. So if you want to get a head start on that, I recommend doing so. And that's due on by the end of the 13th. My memory serves me correctly. So I wanted to recap one quick thing from last day, because last day I started talking about this array-based version of a heap. And recall, a heap is a special kind of binary tree that maintains two properties. There's this heap order property that if I look at any one of my nodes here, if I look at its parent, this key better be at least as big as this one. This is true for every node except for the root. The root is, by inference, is going to always have the smallest value for its key. Now, this is what we called a min heap. So minimum heap. In contrast to maximum heap, you just flip what I just said and you'd keep the largest key in the root and everything will follow the other way around. So at the end of last day, I talked about how you can use an array to represent a heap. I wanted to do an example with you. That way we have a good idea what I mean by this. So this is a very nice classic way of implementing a binary heap. So what you do is you take an array. Keep in mind, there is an advantage to doing this. I'm going to talk about one neat application of using an array-based heap like this. Is that the root is always going to be stored in the first position. Note there are variants of this that put it into literally the first position. I prefer showing you this version where it's literally at the beginning. But there's really not much of a difference. If you ever encounter it, everything I'm just saying, you just add 1 to it, or you just shift everything by 1. But anyways, if you ever find yourself wanting to know what the root is sitting right here in the first position of this array. So there it is, there's 5, there's the root. If I ever want to get the left child, I told you a much more general form for this, just in case you're doing this with a literal tree, or you want to do what I just described, where you imagine you have it where you want to map some structure between the elements in their positions and some other function. So the much more elementary way of going about this, and this is probably an easy way to remember this. So instead of thinking about the function f, you could just think of it as, okay, if I give you a position I in this array, and I want to know where the left child is. So for example, if I look at the root, its position is 0. So if I compute 2 times 0 plus 1, I get 1. And so that's the left child of 5, and it's right here. Do the same thing. If I look at the right child of position I have 2 times 0 plus 2, which that means it's 8 here. And there it is right there. And I could do this for any element here in this array. If I want to figure out if it has a left child, for example, or if I want to know where it is in this array, I can easily compute it this way. So one other remark about this is if you want to know what the parent at a given position, so for example, if I was at, say the very end here, say in the last element, which would be, if I think about all my elements and n is the number of elements I have, I would assume that, okay, well, the parent, so if I have n elements, last position's in n minus 1, it tells me, okay, if I have position n minus 1, and I subtract 1 from that, that's n minus 2, right? Then I divide it by 2. I take the floor of that. Floor means round down. So whenever you see the square brackets, sorry, the square brackets, the brackets like this, that means round down. So you can think of it as integer division. So let me see here. So if I have position 12, I take off 1, I get 11. I divide it by 2. I should expect something slightly bigger than 5, but not quite 6. So if I round down, if I go so I have 12 minus 1 divided by 2, I should get like 5 point something. So I round that down and I get position 5, which is right there. So I could do this for any one of the nodes in my tree here. So you can think of it in like literally like a bunch of links of a tree, just like you would implement a binary search tree. You could do that, or you could think of it like an array, like this. So this is a tree-based representation of this array. So as soon as you see this direct connection, hopefully this is clear to everybody. So if ever I want to compute the left child, I just compute this very basic formula, 2 times I plus 1 if I give you position I. I do 2 times I plus 2 if I want the right child. And if I want the parent, I could just simply just take 1 off that position, divide it by 2, and round it down. So it's a really nice, and the great thing about, I must remark that this way of representing a binary tree isn't exclusive for heaps. So if you really just felt yourself like saying, hey, look, can I do this with just any binary tree? And the answer is, of course, yes. You could do that with any binary tree. Just the thing that makes the heap really nice is notice all the elements are all going to be contiguous. They're all going to be all together like this. If you try doing this with an arbitrary binary tree, you might find there's going to be gaps in here where there's going to be spots with no elements in them. So I'll let you think about that. But are we okay with this array-based version of a heap? So just think about how these two relate with each other. So remember, if you look at this one, think about where their positions are. And now I want to mention one other thing. This is probably the most important thing I can tell you about how you could read off this array. And this will make it much easier for you to visualize this when you look at the actual tree. So if you look at it as the tree, notice I start at 5, then I go 6, 8, 7, 10, 12, 11, 14, 22, 18, 17, 15, 13. If you look at this, you'll notice that I'm actually reading the elements from left to right in this array. So notice that if I read the tree level by level, I read 5, 6, 8, 7, 10, 12, 11, 14, 22, 18, 17, 15, 13. So notice if I read level by level, left to right, I can actually get the entire readout of what the array should look like. Does everybody see that? Isn't that kind of neat? So that's a neat fact about this array-based implementation. And it makes it easier for you to think about what that tree would look like. So are you all good with that? I just wanted to make sure that we're clear on what I'm doing with this array. But like I said, you could do this with any binary tree. Just the heap is going to have a very nice property that everything's going to be all smushed together like this. That's why I want to keep all of the elements. So notice that that's why I want all of them on the last level to be smushed as far left as I can, because that corresponds in my array to everything being contiguous like this, meaning they're all right beside each other. There's no gaps. If, however, let's say this was right here, notice that this would have an empty spot, and that would correspond to a gap in my array. Okay, so now I want to talk about operations for our priority queue. Remember, the whole idea why I wanted to show you this binary heap was because I wanted to implement my priority queue. And I claimed that there was some way I could do that with heaps. So we're going to go through the operations. So the first thing I should point out is that I'm going to keep track of the size of the heap. And I'll do this as I do insertions and removals. So if you're thinking about size is very simple for me to do. It's no different than I did this with the doubly linked list. I just keep a counter. And as I do insertions and removals, I update this counter. So that's one thing. isEmpty, again, if you have at least one element in your heap, that would correspond to your size being, of course, so if it is empty, then your size is 0, right? However, if it's not empty, then your size is at least 1. Of course, you can always just examine the first element, which would be in the first position of your array, and just say, hey, look, is there something there or not? If there is, then you know it's not empty. So I want to focus on insertions and removals then, because those are actually the two main ones that I really think. So we have to be a bit careful with these. So I'm going to talk about insertion first. So what I'm going to do is I'm going to imagine I take my key value pair. So keep in mind when I drew what I have here on the board here, I'm just looking at the keys, which are priorities. And I'm going to imagine I create a new node. So it means I'm going to increment my number of elements that I have by 1. And what's going to happen is I'm going to place this at the deepest level of my heap, and I'm going to smush it all the way to the left as far as I can. And then what's going to happen is we're going to do this bubble up process. Now, you might ask, Dan, what the heck is a bubble up? I'm going to show you through example, and this should hopefully make the idea very nice and clear for you. I'm going to have the pseudocode for bubble up in the notes. It's actually not too bad, but once you see the picture in the example, it should click quite nicely. So what I want to do is I want to do an example with you where I'm going to insert. So I'm going to try inserting. So I'm going to insert. Let's see, I'm going to insert an element with key 3. So imagine I have an element that I'm going to put in, its key is 3. So what am I going to do? I'm going to include it in my array. Now, like I said last time, I'm going to always assume I have enough space in my array to fit everything. So I'm going to assume that there's more elements I can have over on this side, but they're all vacant. So I'm going to place 3 in this position right here, because notice that is my next free spot. I'm going to put the 3 right here. But where does that correspond to in my heap? So you have kind of 2 choices, really, if you think about it. Okay, this is all full, so it can either go to the left child of 11 or the right child of 11. Where should it go, left or right? Tell me, left or right? Left or right? Left, left. Very good, very good. So when I do this, so now 3 is going to be the left child. And now what we're going to do is we're going to do this bubble up process. Now, the way I like to imagine this is, imagine you have like a bathtub full of bubbles. And I'm sure many of you will be familiar with the concept of buoyancy. So imagine I have bubbles and say some are more dense than others. And what happens with the less dense ones? They get shoved up from the more dense ones. So they move their way up. So you can imagine this bubble up process as, say I have this node right here, and it has a key that is smaller than its parents. So does anybody see a way I could fix this? So for example, you notice that this does not maintain the property that I had before, right? So I want to imagine I have 3 and I want to try to see where it fits in this heap. So I'm going to imagine it can kind of gravitate up like it's in a bathtub. So it could go up or down. But I would like it so that I can maintain that heap order property, right? So I want to make sure that there is something here on the left side, but I also want to make sure that this key is somewhere it's going to fit with, such that I'm not going to have this out of order like this. So what I'm thinking about is maybe what I should do is look at this, because if you really look at this picture, you notice that this is the right structure to have. This is exactly the right structure I want to have. However, just the elements along where I could go from 3 up to its ancestors is out of order. So notice it's 3, then 11, then 8, then 5, right? What I would like it to be is that it's 3, then 5, then 8, then 11. Because you notice that if I were to do that, then I could guarantee that this 3 will definitely be, it's not going to be more than 5, right? And same thing with 5 being compared to 8 and 8 compared to 11. So does anybody have any ideas of what I can do with this to maintain the structure, but also fix where this 3 is positioned? So think about it like I'm trying to move the 3 up the heap. Swap them. So somebody had the great idea in the chat. Yeah, you swap them. So watch this. So the bubble up process will work like this. So what I'll do is I'm going to perform a swap. So I'm going to swap. So I'm going to swap 11 and 3. So in the array, this would correspond to me taking 3, and I put 11 here. And remember, like I said, you could compute the position of the parent. So you could easily figure out, like if I'm right here, so I know where this is. What I could do is I could compute its parent, and I could compare it against their keys. If I know that the one key is larger than the other, and it happens to be the case that my parent is the one with the larger key, I better swap them. So So notice I could just swap them like this, but am I done yet? Think of it like this 3 is like a bubble in a bubble bath that could you'll notice that everything around it is still way more dense than it. So it better go somewhere. Is it going to go up? Does it need to go further up? Is it going to go further up? Are we good here? Yes, it's going to go up. It's going to go up. So now I'm just going to do the same thing. I compare 3 against 8. And I'm like, okay, well, look, 8 is much bigger. It's definitely bigger than 3. So I better swap them. So I get 8 and 3 like this. So let's look at our 3. So 8 gets swapped with 3. And now look at this. We could do the same thing here. Yeah, exactly. Exactly, Laura. Very good. Very good. Very good. So you would swap 3 and 5, right? There we go. So you get 3 and 5. You'd swap these two. 3, 5, and boom. Look at that. Now, is this a binary heap? Is this a binary heap now? The answer is, of course, yes. Look at it. Look. Now, you might ask, Dan, how do you know that this works? Like, how do you know that when I make these swaps, I'm not going to mess anything up? Well, think about it. Think about it. Okay. When I made this swap, I did it because this key was less than this one. Now, when I make this swap, notice it's the only node here. Of course, that's fine. But notice that I can have other nodes in my tree, right? But here's the thing. Remember the heap order property. Remember this. Okay, so remember this node's key is going to be, it's not going to exceed any of its children, right? So if I encounter a key that is in fact less than it, and I replace them, say for example, our example with 3, when I had 3 here and I had 8, notice that 8 was in fact less than 12 and all of its children, or its descendants to be more precise. But when I swap them like this, notice that because that key's value was indeed smaller, I didn't mess anything up because it would have anyway been that this one would have been less than all of the descendants of all of the nodes in that tree in terms of its key value. So have I convinced everybody that this bubbling process won't mess anything up? So whenever I do a swap, I always replace it with a key that's smaller. That's how we know it's going to still be fine. So the great thing about the insert is it's really simple. So here's the pseudocode I have for insert. So all you do is you increment your counter for the number of elements, then you insert it into the last position of the position for which there's the next available spot in your array. So you put your element in there, and then you perform this bubble up procedure from that position. So you could figure out right quickly where this is. It's always the next available spot in the array. And then all you do is you do the bubble up from that position. That's it. But yeah, I'll have the pseudocode for bubble up in the notes, but I want you to think about the analysis here. So I want to do this with you here. I'm going to have a more thorough explanation in the notes here with you, but I think quite quickly you could probably see what the worst case time complexity of the insert operation is. So think about it, just like in my example here. So first question I have for you is, what's the height of a heap? So remember, what's the height of a heap? What is it in terms of big theta or even big O? So what's the height? So remember, we said this last day. The goal was that we always want to maintain that this structure stays as a heap when we're done modifying anything. So every time I do an insert operation, it better be a heap. Whenever it's logarithmic. Perfect. So the height is always that in a heap. So what I do is I perform these swaps. So you would agree with me that, okay, doing this takes constant time. That takes constant time, assuming, now I must stress that when I do this step, I'm assuming that the array has enough space to put it in, right? If there wasn't, I would have to perform an array resize, right? Just like what we talked about when we did amortized analysis, you would have to do it there. But watch this. I just do this bubble up process. But what I did with the bubble up process, all I do is I start at that one position and I just swap them if there's ever a spot for which I can perform one of these cases, right? Where I can see if there's a smaller key, I perform the swap. But I know, but watch this, because this is what bubble up actually does if you look at the pseudocode, is I would start off at that position, say that when 3 was right here, all I do is I compare it against its parent. And I just have a while loop. And I just see, is the key of my node smaller than my parents? And I can evaluate each one of those in constant time, each one of these swaps. So each swap is going to take constant time. That means how many times can I perform a swap? Well, it depends on the height of the heap. But what's the height of the heap? It's big theta log n. So each one of your comparisons or swaps takes constant time. And your height of it is overall logarithmic. So it means, what is the worst case time complexity of the insert? Somebody tell me in the chat. So what's the time complexity here? Yes. So notice that this should take you logarithmic time. Isn't that kind of slick? So we're using the structure of this array to easily compare all of our elements. Now, if you're doing this with, of course, a linked structure, it's very much the same idea. The difference is that the implementation is a little bit more complex. It's much harder. It's a little bit more tricky than just this. But you could effectively do the exact same thing. So are there any questions about the insert? So that's really all I have to say about insertion. It's actually quite nice if you think about it. This process of this bubbling up process. Do we need to have the tree drawn out? Well, I'm just drawing this tree to help visualize what happens in the array. So in the algorithm, you would have this array, and that's the one you're modifying. This is meant to show you the tree representation of this array. Now, if you literally implemented a linked-based structure, just like a binary search tree, you could do this. You can do the same thing with a heap, and this would be what it would literally look like if I was doing this. But with that being said, I want to talk about removeMin, because that is easily the one that, if you think about it, it's like, okay, well, because remember, when I put that into that last position, I have this nice bubble up process where it's quite clear I always have one parent that I swap with if I need to. But if imagine if instead of bubbling up, I bubble down, it's not as clear what I should be swapping, if you think about it in that way. So let's talk about how you do a removal in our binary heap. So I want to give you just the general gist of this. Let's talk about removeMin. Now, naturally, just getting the min is as simple as just plucking off like just returning the first element, right? That's all you have to do with the array. It's really nice and simple. However, when you remove it, we have to be more careful. So all we do is we simply remove, element kv from the first position, a sub 0. Now, when you're done this process, you actually return that. Then, now you ask Dan, like, what do we do with the structure if I remove the root? Well, we need to still maintain the structure somehow. So I have an idea for you. What if I take the very bottom, like, because you know I have my tree where it goes level by level, and on the bottommost level, I know it's going to be, it might be partially full, and there's going to be furthest to the left nodes in the tree, right? So what my idea, this is an idea I'm suggesting that we should try doing, is take the rightmost on the bottom level, grab that one, throw it into the root, and see if we can fix up the ordering of the elements in the heap. But notice that if I do this, the structure should look fine. I just have to fix up the ordering of the keys. So just to be clear, what I'm saying is, okay, so imagine it looks something like this. This is just a little doodle. So say it looks like this, and I get rid of this. Some goblin comes and takes this, and is like, ah, it's mine. It's mine. And they take away your element, the minimum. What happens is, I'm suggesting you take this one, and you move it up to the root, and you would agree with me that this would maintain the structure that each level, one after the other, except for the bottom one, is full. So all the ones on the bottommost level are going to be shoved to the left as much as possible. So if I do this, this will assure that this won't be a problem. So then what I'm going to do is I'm just going to copy a sub n minus 1 into a sub 0. But as I said, the heap order property may be violated. The heap order property may be violated. So we may bubble down. We may bubble down the element now. The element now in a sub 0 to a spot that says that. That's a Friday that. that maintains the heap. So does everybody understand the plan? So when I move this element up here, I don't necessarily know where it's supposed to go. So I'm going to do this, what I'm going to call a bubble down process. And you've got to imagine that the element is now, could potentially be heavier or more dense than all the objects around it. So you got to imagine it's like sliding down the tree to the spot for which it could take its most heaviest form. So it's just going to work its way down. But we have to know how to do that. We have to be careful because before we had it where we had one parent and it made it very easy to know where we're going to swap. Now it's not so clear. So there's kind of two things you got to keep in mind. So if we are considering a leaf node, no more is needed as it's a heap. So it means I only have one element. That's what I'm saying, is that this element that I moved up here, that node is in fact a leaf. That means it's already a heap. So now we have to consider the case when I have more than one element. If there is more than one element, so when there's more than one element, that implies the existence of a child. Beginning at the root P, we consider it and its, and a child, because there might be more than one, right? We just know there's at least one. and a child node C of P. So I'm going to call it C, and we're going to have two cases here. So if P has no right child, then C is the left child of P. And so automatically, if there is one to the left, that guarantees it's going to be the left child. However, it might be the case that there's two of them. So if P has both children, you might ask, okay, well, which one should the heaviest route take? Well, you should think about it by trying to swap the one with the smaller key. That's what I'm going to suggest we do. If P has both children, that's both children, then C is the child with the smaller key. So you might ask, okay, well, what do we do with this now? You're going to do, now that I've told you an exact way to determine which child to select, I'm going to do the exact same idea I did over there with the insertions. So remember I did the swaps, but now it's just from top to bottom. I'm just going to follow a path that depending on which of these two cases happens. And if I hit right here where I have a leaf, then there's no more that needs to be done. If the key, so it says if the key of P is at most the key of C, then the algorithm terminates. So it means we're done, as the heap order property will be satisfied. How do you know that? Well, think about it. If I found a place where the smaller of the two keys is in fact going to be like it does, my current one in my parent, and I look at the children all have ones that are going to be at least mine, implying that they're like it all is that if I look immediately below it, that the key's value is in fact larger, or it could be equal to my current one. So if I get here, then we're okay. Otherwise, we're going to do the swap. Otherwise, swap the contents. Swap the contents of C and P and repeat the process as if C were P. So you just reassign what P is to be C, and you'd repeat this process as I just described it to you. So it's either going to be at a leaf, or you're going to have at least one child. And if you have at least one child, then you're going to consider these two cases. And the general way you do it is if you have only one child, you automatically pick the left one. Because if there isn't a right one, then you know there's a left one. However, if you have both of them, you always pick the one with the smaller key. And then if there's a matter, you could swap them. So you maintain the heap order property or get you one step closer to that. You make the swap, and then you're going to reassign P to BC, and then you just go through this process again. So you can see how this can be written as a while loop. So in the pseudocode, it's actually a while loop. So I just wanted to describe it to you because I'm going to have the bubble down pseudocode in the notes, but I want to describe removeMin to you. So let's do that. So I want to do an example, and I'm also going to describe the pseudocode here for you. So everybody has an idea of what I'm talking about with this. So first, are we okay with the idea? So instead of bubbling up, we're going to bubble down. And this bubbling down process just simply means I'm always going to take the smaller of two keys that are potentially my children. I'm going to pick always the smaller when I perform a swap until I get the heap order property. Okay, so question, would the algorithm hit the fact it is a leaf? Would it terminate or repeat? So if you hit a leaf, so just think about it. So each one of these is a leaf. So if I'm right here and I ask, okay, well, like, do I have any children? The answer is I don't have any children. So if you think about it, if say P becomes a leaf, then you know right away, hey, look, I have nothing I can do because I have no more children. So in that case, you're done. Like, you already have the heap order property satisfied. Hey, no worries, no worries. No, these kind of questions are helpful because other people might be thinking about it too. So I appreciate these kind of questions. So let me just quickly write out the pseudocode for removeMin. This one I'll be a little bit more careful with. Again, I'll have a little description in the notes for you. So this is removeMin. It has no inputs. There is no input. There's none. Output. So it removes element with minimal key from A. Null if empty. So remember, if there are no elements, you better return null or something. And of course, we maintain that's a heap. We're going to maintain heap. We want to make sure we maintain those properties. So naturally, if you have an isEmpty method or function, depending on how you're doing this, I'll just assume it's a method. So if isEmpty, then you could just simply return null. Now, I just do exactly what I said before. I determine the minimum is always in the first spot. So I'm just going to say that the min element is, in fact, in that first spot. So I call it min elem. That's going to be a sub 0. And then what I'm going to do is, because I want to hang on to it, because it's probably going to be a reference or a pointer to that object, or it could be a value. It's okay. So I'm going to reassign a sub 0 to be a sub n minus 1. That would be the position of, say, the rightmost element in my array. So like that one. And then I decrement n, the number of elements I have. And then I'm going to perform bubble down. This bubble down procedure has two parameters. It namely has a starting position. This is going to be the position of the node in that tree. That is going to be the one I need to bubble down. So that's what the first parameter is. So I know I need to bubble down the element in the first position, which is position 0. And I need to give an end index to specify where the array, where I need to look ends. If you look at the pseudocode after class, you'll see what I mean by this, because we need it for one of our applications a little later. But obviously, I don't have to look any further in the array than position n minus 1. So this is a pretty good end index for me to use. Just keep in mind, I did decrement n by 1. So this will, for sure, if I had one less element here, this will definitely keep everything together. So this is just the interval I'm going to be interested in. And lastly, of course, you just return min element. So you return min el. So this is removeMin. Like this looks really nice, right? The bubble down, it looks a little uglier, but the concept of it is actually quite nice and simple. So I want to do an example here with you. Let's do an example. So I'm going to take my example I have here. And let's use this one. So let me see where I have my example. So I want to make sure I pick the right key for example. So insert Okay. I think technically I have it. I think I reset my heap, but that's okay. What we'll do is we'll work with this one. If you could always take the one in the notes as an extra example. So that's even fine. So what I'm going to do is I'm going to, when I do removeMin, notice that I'm going to then take, this one right here. 5, 6. Actually, I think we're okay. Yeah, I think we're okay. Yeah, this is the same example. My apologies. No, wait. No. We're going with this. Let's go with this. Sorry, I'm getting really excited about doing this with you because it's always fun when I do this for the first time with students. I get to do a lot of this with my hands. So anyway, so if I do removeMin, what happens is, okay, well, I'm going to take 3 along with its value. So this is min LM. So that's out here. I'm going to take 11. I'm going to put this up into the root like this. And now naturally you say, okay, well then, so now remember in terms of the tree, so if I look at this, so 11 is now over here. So 11's right there. Notice I have nothing right here. That's okay. I've removed one element. So as far as we're concerned, this doesn't exist any, like if we remove this, it's gone. We don't need this anymore. Because I removed one element. So what do we need to do? So I've done everything up to this point. I imagine I decrement my number of elements by 1. And now what I have to do is I have to do this bubble down process. So I have to be a bit careful about this. Okay, so I have 11. And now what I do is I have 2 children here. So do I take 6 or 5? Somebody tell me, 6 or 5? Well, you have to pick one of these two. You have to pick one of them. 5, yeah, you pick 5. It's the lesser of these 2 keys. Because there's 2 cases. Remember, there's one child that guarantees it's going to be on the left. If there's 2 of them, then it means I have to pick the lesser of these 2. And then I compare them. 11 versus 5. I better bubble down this. So now let me take the 5. We're going to move the 11 down. And 5 is going to come up here. See, like I said, I get to do this with my hands. It's the best part of this. So 5 is now in here. 11's right there. Okay. So are we okay yet? Swap 11 and 8. Yeah. So notice now I have another case. I have 2 children like this. I take the lesser of these 2 keys. It's the right child. I compare 11 versus 8. Oh yeah, well, 11's definitely much bigger. It is much bigger than 8. So I'm going to swap these 2. So I'm going to swap them. So remember, I'm just swapping these. So now I have 11 here, and I have 8 here. So so 8 goes over there. And now, am I done? Am I done? So, am I all done? Yes, I'm all done. Look at that. So now look, now I have maintained the heap, and we're all good. In my notes, I have another example with the original tree where I make a small tweak. You can give that one a try as well if you find yourself a little uncozy with this. So remember, in bubble up, I always have one parent, so I'm just swapping directly with my parent. When I bubble down, I have 2 cases. Either, well, actually, technically, I can have it where I'm at a leaf, meaning that I have no other stuff I need to do. Like over here, I'm all done. However, if I have at least one child, you know it's going to be immediately on your left. That's because of the heap order property. And it's a nearly complete binary tree. So it's a complete binary tree property we're using. And then, of course, if there's 2, then you just pick the lesser and you swap it if it indeed is the case that they need to be swapped. So are we all good with that? Okay. So let's do the time complexity analysis of this. So it's going to be very similar to the insertion. So checking if it's empty, like I established earlier, this takes constant time. So I'm just going to keep it nice and short for everybody. So just because I like to keep an eye on the clock. So I could do this in constant time, right? I could do that check. I could do all of these updates right here and the return all in constant time. Now this is under the assumption that everything in my heap all fits, and indeed in the case when we remove, we never add more elements, right? So we never have to worry about that in this case. That's only when we have an insertion that we have to worry about that. So just, that's something to keep in the back of your mind is if, say, for example, you need this array to get resized, you have to keep that in mind. In this case, you don't have to worry about it, right? Because we're never actually introducing another element, it might shrink. However, if you have some resizing scheme where if the array gets too small, you might have to end up resizing it to a smaller size. So that comes into the time complexity if that matters. In this case, I made the assumption that it doesn't. So next is bubble down. That's the only part I haven't really addressed, right? So it's quite similar to what I did before. So notice that, remember, what's the height of a heap? What's the height of this? Remember, it's big theta. What is it? Come on, tell me, tell me, tell me. What's the height of a heap? Yes, perfect. Perfect. Yeah, logarithmic. It's big theta log n. And that's why we want to maintain this heap order property and, of course, the complete binary tree property. If we have both these properties, we can guarantee that. So if we have both of these, and I know, okay, so now I have to do this bubble down process, doing two comparisons like this, notice that well, first, each one of those cases I can check in constant time. If I need to do a swap, it's just, I already know how to compute the right child or the left child once I've determined which one is C. Once I do that, I can do a swap. That takes constant time. So it only depends on the height of the heap. So this part right here, of course, this takes big theta log n. So the nice fun thing is that removeMin, this is going to end up being the time complexity is big theta log n. So that's your time complexity. Notice that all these constant functions get dominated by, in fact, the logarithmic one. That's big theta log n. Perfect. So is that wonderful? So now notice, so I just want to summarize this, seeing as this is actually the perfect place for me to do this. Let me just summarize this for you. So okay, if let me just do it over here. I want to draw you one quick table and then we're done for today. So just a summary. So min is empty and size. So if I look at my methods all of these can be done in constant time. If I have my insert takes big theta log n. This is all under the assumption, of course, that everything fits in my array. And of course, removeMin. This is big theta log n. So as I wanted to remark, remember, I can implement this binary heap as an actual tree. And this assumption that I made about the size of the array goes away completely. But I must stress one thing. Remember I talked about amortized analysis? It must be stressed that if you think about it in terms of amortized, all these results are actually true amortized. If you're actually talking about it more generally. So I'll let you think about that. So this is a perfect place for me to stop. So next time when we come back, we'll look at some things we can do with heaps beyond just being a priority queue. That being said, I want to say thank you very much and have yourself a beautiful day. And have a good weekend. I'll see you later.